Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video provides additional practice using corrections for sample size. Let's get started. So to start off with, let's look at a Coca-Cola bottling facility. This facility is filling cans of Coke so that the actual amounts have a mean value of 12 ounces and a standard deviation of 0.11 ounce. So the question we're asked is, what is the probability that a randomly selected can of Coke will have at most 11.8 ounces? Go ahead, stop the video here, get into StatCrunch, work this problem, and then come back and we'll see how well you did. Okay, so in StatCrunch, you should have the normal calculator, putting in your mean and standard deviation values that they give you there in the problem statement. We want the probability that we're going to be at most 11.8. So that means we're going to be less than or equal to 11.8. So I make sure that's selected here in my drop down. 11.8 is my random variable. Hit compute, and out comes the probability that I'm looking for, which is about 3%. Now, what is the probability that 36 randomly selected cans of Coke have a mean value of at most 11.8 ounces? Again, get into StatCrunch, stop the video, get into StatCrunch, and then come back and we'll see how well you did. Okay, let's see how well you did with this. Here's the normal calculator in StatCrunch. Remember, since your sample size is greater than 1, you've got to adjust that standard deviation value. So we have 36 in our sample, so the square root of 36 is 6. I take the 0.11 that was given earlier, divide by 6, and that gives me 0.0183, which I put there into my standard deviation field. And now I hit compute again, and now comes a really, really small number. I mean, 5.2 times 10 to the minus 28. Okay, that means there's 27 zeros in between the decimal point and this first non-digit 0, which is a 5. That's a really small number. So it's a practical, it's practically certain that, it's not going to happen. Okay, it's practically certain that 36 randomly selected cans of Coke will not have a mean value of at most 11.8. So, based on these results, do you think customers are being cheated? Go ahead and look at what we've got here. Look at your different probabilities, and then decide, are customers being cheated? What say you? Okay, well, hope I hear you say no. Okay. Here, we're seeing a almost certain, I mean, this is practically 0. So the probability that these cans are going to have less than the 11.8, 36 of them, is going to be like, it's almost certain it's not going to happen. So it's actually going to be certain that you're getting more than 11.8. They're actually giving you more, closer to that mean value of 12. So no, it doesn't appear that customers are being cheated, because the probability is saying that it's actually going to be closer to that original mean value that we saw here. Now, if it were going the other way, if it was certain that they were getting less, then yeah, you probably would say that you'd be cheated. But that's not the way it is. It's actually flip-flopped, so it's going the other way. So the probability they're getting less is not that great, and therefore they're not being cheated. Let's look at our final problem involving Mensa. Mensa is basically a club for people who are super smart. Okay, they score top scores on IQ tests. So in order to get in, you've got to have a score in the top 2% on a standard intelligence test. So the Wechsler IQ test results in normally distributed scores with a mean of 100 and a standard deviation of 15. So here we've got 4 questions to answer. First, what is the minimum score on the Wechsler IQ test that meets the Mensa requirement? If one randomly selected person is selected to take the test, what's the probability that person will meet the requirement? If 4 randomly selected people are selected, what's the probability their mean score will meet the requirement? And if 4 people take the test and their scores have a mean of 132, but we don't know what the individual scores are, can we conclude that these 4 subjects are all eligible for Mensa? So go ahead, stop the video here, and then try this out. Try to see if you can work this out. And then come back and we'll see how well you did. Okay, let's see how you did with this problem. So to answer these questions, there's 4 of them. Let's tackle each of these questions one at a time. So the first question we're asked is, what is the minimum score on the Wechsler IQ test that meets the Mensa requirement? So to answer this question, I'm going to go into StatCrunch, and I'm going to stick in the mean and the standard deviation values that they give me. I want the probability that I'm going to get over some random variable. I don't know what that is. That's the minimum score they're actually looking for. But I know it's in the top 2%. The top 2% here on my distribution. So I want this right tail, and I want the area of that right tail to be 2%. So that's where I get the 0.02 coming in here from. And I want it to be greater than, so I can get that right tail area. Remember that inequality sign is like an arrow. It's pointing to the right because I want that area in that right tail. So when I hit compute out of that, out comes the 130.8 that you see here for your random variable. This is the score, the minimum score that you have to have on the IQ test in order to meet the Mensa requirement. Second question asked, if 1 randomly selected person is selected to take the IQ test, what's the probability that person will meet the Mensa requirement? Well, that's just going to go back to 2%, right? Because the requirement is to score within the top 2%. So if you put this value back into StatCrunch, out's going to come 2%. So that's just what it is. So you just come back, you're in the top 2%. That means there's a 2% chance that you're going to be in that part of the distribution. Third question, if 4 randomly selected people are selected to take the IQ test, what's the probability their mean score will meet the Mensa requirement? So here for this question, I'm actually going to go back into StatCrunch, get that normal calculator, but I'm going to make an adjustment to my standard deviation value since now I have a sample size greater than 1. So here we have 15, which was our original standard deviation, divided by the square root of 4, which is 2, and that's going to give me 7.5. So 7.5 is my adjusted standard deviation value. When I hit compute again, out comes a really, really small number. So the probability that 4 randomly selected people are going to have a mean score that meets the Mensa requirement is, it's almost certain not to happen. That brings us to the last question. If 4 subjects take this test and their scores have a mean value of 132, but we don't know what the individual scores are, can we conclude that all 4 of them are eligible for Mensa? Well, in this case, the answer is going to be no. Remember, the mean is simply an average. So, we don't know what the minimum and the maximum values are going to be for that range of values that we have. So, yeah, they could be, but, they also could not be, okay? If you have all the scores that are the same and all of them meet the requirement, then yeah, okay, you could say that all 4 of those subjects meet the requirement. But you don't know that that's the case. Maybe some of them scored really high and others scored really, really low. And when you average everything out, the average meets the requirement, but there's some of those that scored really low that won't meet the requirement. So without the individual scores, you can't really say how many of them are actually eligible for membership in Mensa. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.